session under Unit 4, I'm going to be looking at unsaturated heterocyclic compounds. So in the previous slide, in the previous session, session 2, we looked at some saturated heterocyclic compounds. Now, in this session, session 3, we are going to look at unsaturated heterocyclic aromatic compounds. So at the end of the session, you should be able to provide names for some given unsaturated heterocyclic compounds. You should be able to draw resonance structures for furan, pyrrole, and thiophene. You should be able to explain the basicity in pyrrole, and lastly, you should be able to compare the basicities of pyrrole, furan, and thiophene. So we'll typically begin with nomenclature, and we're going to look at the nomenclature of these heterocyclic aromatic compounds: thiophene, furan, and then pyrrole. Now, nothing changes with this. These heterocyclic compounds have their common names, the parent name being the furan, thiophene, pyrrole. So basically what happens is whenever a substituent is added, we number it in such a way that we start with the heteroatom as number 1 and move around the ring with a substituent number for our substituents being smaller, right? So we know of this basic approach. So in this case, you count anti-clockwise. Your heteroatom becomes 1, 2 becomes the methyl group, so you don't count the other way around the clockwise, but you count anti-clockwise for this to be the 2-methyl. Similarly, the same thing happens here. So you count giving the heteroatom the number 1, 2, 3, so 2 chloro and 3 bromo thiophene. Now, in cases where the heterocyclic ring contains more than one heteroatom, naming follows the same order just as it was considered under the saturated system. So, just as we considered in the saturated system, oxygen is considered first, followed by sulfur, and then nitrogen. However, other things being equal, numbering preferably commences at a saturated rather than the unsaturated heteroatom. So in the case where you have the same heteroatom present in the ring, then we look at the unsaturated, give it precedence over the saturated. So you realize that this nitrogen is unsaturated, is bonded to one nitrogen, single bond, another carbon, single bond. However, the nitrogen number 2 is bonded to carbon in a double bond, bonded back to its another nitrogen in a single bond. So this becomes the saturated and this becomes the unsaturated. So we give the preference to the heteroatom with the unsaturated bonds. Similarly, in a case like this, between thiophene, sulfur and nitrogen, we consider the sulfur first before the nitrogen. So numbering starts from the sulfur in anti-clockwise direction. Lastly is to look at fused aromatic systems. So the side of the ring that is being attached to another ring is named with alphabets, right? So we use the numbers for the atoms, and the side of the ring is numbered using alphabets, right? So for fused rings, the side of the heterocyclic ring is labeled by the letters A, B, C, etc., starting from the heteroatom or the atom number 1. This becomes number 1, 2, 3, 4, 5, 6, 7. You see that 6, sorry. And therefore, the side A is between 1 and 2. So if you number this 1 and this carbon as number 2, now the A becomes the side between A, 1 and 2, and B becomes the side between 2 and 3. So let's look at typical examples. So we have our parent's common name known as furan for this 5-membered ring with the heteroatom oxygen. So this becomes number 1, this becomes number 2, number 3, 4, 5, 6, 7, right? But our alphabets go the other way around. So we have 1 here, we have A, you have A here, then you have B there, you have C there, you have D there. So A, B. So the benzene ring is attached to the furan ring on the side labeled B. So the name is given as B furan. Similarly, if we come to thiophene, we have our S as the number 1. So this becomes A, this So the benzene ring is attached to thiophene on the side labeled C. So the name is given as benzo C thiophene. The same applies to these other examples. You can apply them in this all these examples. Now, if you want to look at the aromaticity of these five membered ring unsaturated heterocyclic compounds, now all the heteroatoms donate 2 electrons to the ring, right? And hence each has 3 pairs of delocalized pi electron. Now, so please let's take note. I think we explained some of these things in the other units. So there are 2 lone pairs of electrons on sulfur. However, only one pair is delocalized, the other is localized. This is especially this pair is not involved in aromaticity, right? So this pair, the 2 pair here and the 2 pair there, are involved in aromaticity. So it has 3 pairs of delocalized electrons. I think we talked about this in the Hackles rule a lot, so we know what the localized pi electrons are. So here we have 2, 4, 6 nitrogen. So in pyro has just 1 lone pair of electron, but in furan and thiophene they have 2 different pair of electrons, right? So these 3, 2, 4, 6 are involved in aromaticity. Then we know that aromaticity is what directly related to resonance. So the more aromatic you are, means the more resonance structures you produce. So there's you learn something intriguing about nitrogen's inability, basicity, and other things is affected greatly due to the fact that in pyro alone there's just 1 pair of electrons. Now, thermodynamic and NMR estimations show that thiophene is slightly aromatic than pyro, right? But then it is far, far more aromatic than furan. And pyro is also more aromatic than furan. That makes sense. And furan is also less aromatic than benzene. So the order of decreasing aromaticity is here. You have thiophene being the most aromatic between the 3, followed by pyro and furan. And even between furan and benzene happens to be more aromatic than furan. Now, the next thing to talk about is the basicity between these 3 heterocyclic compounds, right? So between these 3, let's consider pyro for instance. Now, unlike amines, pyro is an extremely weak base, and it's even sometimes considered as not being a base at all. The reason is that its nitrogen does not have unshared electrons, right? The electrons in pyro, the pair of electrons, lone pair of electrons here, are involved in aromaticity. So the non-bonded pair of electrons is needed for pyro's aromaticity. So it doesn't have any free pair of electrons to be donated as a Lewis electron pair donor, right? And in addition to contributing 2 electrons to the pi molecular orbital, so there are 2 pi electrons here. There are 2 pi electrons here involved in pi bonding. The nitrogen in pyro shares 3 electrons in sigma bond. So there's a sigma bond between nitrogen and carbon here, between this nitrogen again and carbon, between this nitrogen again and hydrogen. So these 3 electrons are involved in bonding together with these 2, which are also used in aromaticity. So as a result, all 5 electrons all 5 of the bonding electrons of nitrogen are used in bonding, right? So all of them are involved in bonding, and as a result of that, it has no pair of electrons to donate to make it a Lewis base. So then again, pyro's aromaticity is destroyed when the nitrogen is protonated, right? Hence the conjugate acid is a strong acid, making the base an extremely weak base. Now, if you want to compare the basicity between pyro and furan, I mean, if we consider the fact that furan has another lone pair of electrons that is not needed for its resonance formation or aromaticity, then it means that furan will be more basic than pyro, because furan will have 2 lone pairs of electrons on its heteroatom, the oxygen, whereas in pyro, the nitrogen has just 1 electron pair, which is even used in resonance or aromaticity. So basically, furan will be more basic than pyro because of the extra lone pair of electron it has that is used as an electron pair donor, making it a good Lewis base, making pyro a good Lewis acid, whereas furan is a good Lewis base. So the order of um, decreasing basicity is furan is more basic than pyro, and then thiophene is the least basic. Now, if you want to look at the resonance energies as well, then here you can even add another 5-membered ring with no heteroatom, even benzene. Now, this is the decreasing order of the relative resonance energies of these 5 aromatic compounds. Now, furan is the least, right? This is decreasing, so furan is the least. This is because it is the most electronegative. It has the heteroatom between all these. This is having a heteroatom, which is the most electronegative, right? And has no vacant d orbitals, and hence will have the smallest resonance energy. So that is the reason why furan happens to be the least among the 5. Now, when we want to consider the 3, just these 3, thiophene, pyro, and oxygen, thiophene has the greatest resonance energy among the 3. The reason is that sulfur is the least electronegative, right? Whilst oxygen is the most electronegative, sulfur happens to be the least electronegative, and therefore its electrons are easily delocalized into the ring to form more resonance structures. So the formation of resonance structures between thiophene and furan, you can see that because the electrons are not held back with strong forces, they are easily delocalized into the ring to form more resonance structures compared to what happens in furan, because in furan the oxygen is highly electronegative, so its electrons are not easily delocalized to form more resonance